Welcome to clickmyproject.com. Here we are going to discuss about synchronous FPGA based high resolution implementation of digital pulse with modulator. In our project mainly focused on the implementation of digital pulse with modulation in mainly digital control of switching mode power supplies and has obtained a great research attention to their now well known advantages such as probability advanced control algorithm, reduced recombinance count, low consensus to external factors are aging ease of design and prototyping, etc. However, digital control design is also well known. The two most important disadvantages are processing sampling delay and limitation resolution. Regarding the second factor, resolution is limited mainly by the analog to digital converter and the pulse width modulation. However, the ADC is becoming is less important problem thanks to the windowed ADC technique, and whereas the pulse width modulation resolution needs to be higher than the ADC resolution for avoiding limiting cycles. Traditional digital pulse width modulation are based on counters. These advantages of these digital pulse width modulations that they are very simple and attain high linearity. However, their resolutions cannot be very high, as the minimum time step is equal to the clock period of the counter. Furthermore, their power consumption is proportional to the clock frequencies in high power consumption. In order to increase the digital pulse width modulation resolutions, delay lengths can be used. In our digital pulse width modulation, a lot of different architectures have been proposed in these years, and even a classification of them appeared. Although all these architectures differ from each other, almost all of them make use of delay lines. The advantages of delay line TPWMs are high resolution and low power consumption. However, they have lower linearity and monometric behavior in some cases. In trying to obtain a trade-off between the advantages of counter-based and digital pulse width modulations, hybrid architectures have been proposed. The higher than the number of bits in the synchronizations, part of the higher linearity achieved. In our to work, we propose a new digital pulse width modulation hybrid architecture. The synchronization block is counter based. However, the asynchronous block is not based on building a new delay line structure, but using this field programmer gate array availability log loops. This is an main importance from previous solutions which developed their own delay or TLL. Almost every FPGA includes TLL block with pulse shifting features. Taking advantage of these resources, the proposed architecture attained an excellent conditions. The proposed digital pulse width modulation is an principle independent for FPGA implementation, and integrated circuit implementation would need the development of TLL with pulse shifting capability, which is the most complex part of the architecture. This is our system flow diagram. This black diagram represents a flow of our operations. First of all, we give the input signal at clock signals only. Now we change the clock signals randomly, consists of zeros and ones. We get the different kinds of output. This output depends on the D flip flop, SR flip flops. They are mainly focused on the D flip flop, give the direct input to the delay. Then finally, we use a TCM circuit, digital counter manipulations and counters, set clock reset. These are the main important things of our input. Finally, we generate the output in digital pulse width modulation. These digital pulse width modulation based on our clock signals and select bit based conditions. In case of select bits are positive, we get the output at positive output. In case of we give the negative select bit, we get the negative output in our program.
Now we are going to discuss about the running procedure of our project. In our project we have four steps. First step we check the syntax error, then second step we generate the Addons schematic diagram, then third step we generate the technology schematic diagram, then finally we generate the simulation waveform. First we select the implementation, select main function, then select check syntax. In this process we check the syntax error of our program. In case of any error and warning there displayed in our console block. Please show our console block. In our program we have no error. Now we are going to the second step. Please select view RTL schematic and run that. Now we generate the RTL schematic diagram. Add then create schematic. This is our overall RTL schematic diagram. TC, clock reset. These three signals are our input signals. TBWM, TBWMP. These two signals are our output signals. This is our internal RTL schematic diagram. Now we completed two steps. Now we are going to discuss about third step. Select view technology schematic, then add, create schematic. This is our overall technology schematic diagram. This is our internal technology schematic diagram. This internal technology schematic diagram consists of number of LUTs and flip-flops. Now we are going to discuss about simulation waveform generations. Select simulation, select main function, then select simulate behavior model and run that. Now we give the input values. Clock value set to 0, reset value set to 1, and TC values give any random input. Then run our project. Then again change the reset value to 0 and clock value set to 1 and run our project. Then again change the clock signals 0 and again change the clock values to 1. Please change the clock values simultaneously. Please change the clock values zeros and ones at randomly, because we didn't get our output. Please change the clock values again 0, then clock value change it to 1. Now we got our final output. This is our running procedure of our project. Thank you.